This video is about bijectivity of a function and the calculation of the inverse function of a given function. So we start with an example. So the function maps from the real numbers to the real numbers and is defined as fx as x squared plus 1. So looking at the sketch, we want to find out, is the function bijective or not? So we draw an xy coordinate system. And you see, if you neglect the 1, this is the standard x squared parabola. So it looks like this. But as you have here the intercept 1, we have to shift the parabola from the origin to 1. So we can scale, label the axis. So if you plug in for x is 0, you get for y is 1, so you start here. If you plug in 1, 1 plus 1 is 2. If you plug in negative 1 squared is 1 plus 1 is again 2. And for 2, it would be 2 squared is 4 plus 1 is 5. So yeah, the slope is very high here. So you come from here, and we sketch the graph. So this is the function x squared plus 1. And you see this is symmetric with respect to the y-axis because of this square here. So looking at the sketch, we see that the f cannot be bijective. It's not bijective. So because it is not a one-to-one mapping. So here, for example, if you would choose, let's say y is equal to, you have two x values. So for one y value, you have x value 1 and x value minus 1. It's not a one-to-one mapping. And as you remember the definition of bijective function, a function is said to be bijective if for every y value, for example y is 2, there exists a unique x. In this case we have two x values, not just a unique one. So it's not bijective. But we simply can make the f bijective if we restrict the domain and the range of this function. And how to do this? In this case, we have to look at the graph, and we choose the right branch. You could also choose the left one, but in this case, we choose the right one. So we restrict f to the right, the branch on the right. So if you look at this, the domain are the x values, and the domain starts from 0 to infinity. I include 0, and it is mapping to the range, and the range consists of the y values starting at 1 and going up to infinity as well. Again, we include the 1. So the description of the function is exactly the same. And this function is bijective now. Now for every y value in this range, there exists a unique x value in the domain such that f of x is equal to y. So for example, if you choose y value 2, you just have a unique x which is 1, if you just consider the right branch. Thus, we now can find the inverse function of these bijective functions. Recall that inverse functions only exist for bijective functions. How to to get this, you start with the equation, but instead of f of x, you write y. And now you express x in terms of y. So y minus 1. And now you get the x, which is simply root of y minus 1. But don't forget, when you consider roots, it can be plus or minus. And with this knowledge, we can write down the inverse function. You have to interchange the range and the domain. So the inverse function now starts using y values. So you start with the range now. Just swap these two to the domain of f, because you get x values out of this. So, and here is the function. Y is mapped onto root of y minus 1, and you take only plus y, because you only have if you look at this, at the range of the inverse function, it is positive, so this must be plus. So this is defined as the inverse function in terms of y. For sure, you can rename this in terms of x. So the inverse function in terms of x, you just write here instead of yx. It's just renaming. It's the same. So now let us try to sketch this in the same coordinate system. The inverse function is mirrored at the identity mapping y is equal x. So we start with drawing y is equal x first. So this is y is equal x, usually called the identity mapping because x and y values are the same, or also called first median because it separates the first quadrant into same geometrical objects. The slope here is 1, so 1 to the right, 1 upwards, and no intercept, so going through the origin. And now we try to mirror this right branch onto here. So this point is here. The 2 should be actually here. So instead of 1, 2, we have now 2, 1, and so on. And you see this is a root function. You can also plug in values. For example, 1 for x, then it mapped to 0. 2 mapped to 1. 3 mapped to root 2, which would be here. So you see here, for example, this point, I want to use the black color, sorry. This point is mirrored here, that one is here. You have a right angle here, or also from here, this is mapped onto this point, and so on. How else can we think of this inverse function? The inverse function, it does exactly the reverse of the function. That is, if you take an x and you map f onto it, and then you map f, the inverse function, f power minus 1, the inverse function f to the minus 1 onto this, you actually get the x back. This is what an inverse function does. For example, just a quick example, 3 power 2 is 9, and if you take the root of 9, you get back the 3. But also the other way around. If you first do the inverse function, and then you map f onto this, you get back x. And also using this example, first root, what can we do? First root 4, which is 2, and then you square the 2, you get back 4. So these examples we don't need anymore. And what we're gonna do now is we verify these two properties. So we do the verification for our function. So we start with the first one. So just plug in f of x from above. Apply the inverse function, which is root. The x value is now not x. The x value is this object, x squared plus 1. You have to plug in this instead of x, minus 1. And now you see, it's really fulfilled because the 1 cancels out and root of x squared is x. I just want to mention that actually the root of x squared is actually the absolute value of x. But in this case, the x is defined on positive values, on the positive range, so we don't need the absolute value. So that's fine. We also verify the second equation. Let's maybe take the fancy color. So this one. So first plug in the inverse function. And then apply f. But the new x value for f is the root. So instead of x, I write root. I have to square it, plus 1. If you square it, the root disappears. And you see what's going on. We get back x.